One thing they represent, that's not entirely what they represent. Ah, so they represent two big things, direction and magnitude. Direction and magnitude. So it's a direction to go in and go a certain distance. We have one that goes from LA to Buffalo. We have one that goes from Albuquerque to Oshkosh, Dallas to Pittsburgh. It's a direction and a distance. It's direction and a distance. So that's what we're working with today. We're working with vectors. We are working with vectors. How many people have worked with vectors before? Potentially. You don't know that. Okay. It's pre-calculus. It's in physics. It's really common. And most of you work with to some degree, maybe not to the same degree as everybody else in the class. First thing about vectors, when you add them, how do you go about adding vectors? What do you do to add vectors, Ali? Okay, so if we had the components, let's say we don't have the components. Let's say we just had pictures of the two vectors. How do you add the two vectors together? It's on the board. You can look at the picture. Explain it out loud using sentences with subjects, adjectives, maybe a verb and two are there. Explain to me, how do you add a word called? You can switch the order of addition, and it's the same thing. What's that called? Do you remember? Begins with a C, commutative property, yeah. So vector addition is commutative, and you can see it here. If we had this vector and we add this vector to it, the resulting combined displacement vector is from the initial point to the last terminal point. What happens if you add them in different orders? What do you end up with? The same thing. What shape is that? It's a parallelogram, so you can prove it's the same thing because it is a parallelogram. You can prove that, but it doesn't matter what order you add vectors in. Can you give me a real-life situation, Ali, that you add vectors in? A little bit more fun when we talk about subtraction. So let's talk about subtraction here. This is one way to think about subtraction. The difference, vector W minus vector V, is the displacement vector that when added to V gives W. This is one way to think about it. So if you have W minus V, the difference between W and minus V is the vector you have to add to V to get W. That is one way to do it. One way to do it. I kind of like thinking of it a different way, but you're going to see this all the time. I like thinking of it as when you subtract two vectors, it's like adding the opposite of V. I like thinking about it that way. If you add the opposite, what happens when you put a negative sign in front of a vector? What does it do? It flips the direction. How many degrees? 180. It's just a 180-degree turn. It goes in the exact opposite direction. So if you end up doing that in this case, if you were to do W plus negative V, you have W, which goes from here to here, but then what does negative V look like? Well, negative V looks like this vector. It's the opposite of what goes on right there. Let me actually do it a little differently. So if that's V right there, here is negative V going in the opposite direction, right? So that's negative V like that. But if we take that vector and we place it right there, what's the resultant vector? The resultant vector goes from here to there. Now, this vector right here, we highlight it appropriately, this vector right here, W minus V, is it the same as this vector right there? It is. It's a parallelogram. It is the same vector. Can the same vector be in a different place depending on its initial condition? Absolutely. I could say go 50 degrees from the horizon at 100 miles an hour. If I don't tell you where to start, it could be anywhere, right? So two vectors can be identical to each other but be in different places. Absolutely. Okay. Zero vector is a real vector. It means you're going nowhere. Just remember that. And here are four vectors. What can you tell me about these four vectors? What are they? They are all what? What do they have in common? They're all what? Multiple in each of these four. What's the scalar multiple here? Negative 2. Scalar multiple? 1 and 2. If the only thing that changes is the scalar multiple, the vectors have to be parallel to one another. Exactly. Scalar means unchanging. It's a set number. Scalars, you'll hear that a lot. So what kinds of questions could you be asked? Let's see if for some reason this is being jumpy today. I'm not sure. Well, first we get to start using some more Greek letters. Anybody know what this is called? Lambda, right? It's lowercase lambda, I think. There's an uppercase. You're going to take future math classes where you're going to run out of letters, so you start using Greek letters, and then you run out of Greek letters, so you start using lowercase Greek letters, and you're like, man, I don't want to do this anymore. So if that's a displacement vector, here are the truths that we have here. The displacement vector, lambda v, is parallel to v pointing in the same direction if it's positive, and the opposite direction if lambda is negative. Yay! The magnitude is lambda times the magnitude of v. Like up here, if we want the magnitude of this, so we know that what's the relationship between the magnitude of v and this one? We know it's half, right? But we don't know what the overall magnitude is. Like, is the overall magnitude 0.5? No, it's 0.5 times whatever the magnitude is of v to begin with. It's not just, oh look, there's the coefficient. What's another way to say the magnitude of a vector? What's another way to explain what the magnitude, how would you explain to like a 5th grader what the magnitude of a vector is? The length of the vector. So in 2 dimensions, it's relatively straightforward because what can you use to find the length of a line segment? No, well, you could use a ruler. No, that's fine. You could use a ruler. It's like my mother has this classic thing, you're like, well, I was taking the SATs, it asked me a question, how long is this line? 2 inches, why? Because I measured it, you know, like, they were looking for something else, and I am too. What formula can you use? What theorem could you use to find the distance between 2 points? Pythagorean theorem, right. So if you have a vector, let's say one of these vectors was say 3, 4, over 3 up 4, that's a vector. What's the magnitude of that vector? Oh, come on, what's the length of that vector? 5. How'd you get that? Why do you know it's 5? Ah, so you did the square root of 3 squared plus 4 squared, which is 5. Nice. The Pythagorean theorem applies. Very nice. Okay, but what space are we going to be dealing with? 3D space. We're going to be dealing with 3D space. 2D space, nah. I'll definitely come up with really awesome, creative, crazy hard problems if you're working in 2D space. But let's talk about 3D. 3 vectors are up there that you're going to be very, very, very familiar with and use many, many times in this class. The 3 vectors are I, J, and K. If you put them in alphabetical order, I is X, J is J is Y direction, and K is the Z direction. What do those 3 vectors up there, I, J, and K, have in common? What do they have in common? Magnitude is 1. They're all unit vectors. They're all unit vectors. What is so special about those 3 vectors? What can you do with those 3 vectors? Use them to find? Use them to, yeah, use them to find what? Yeah, go ahead. Question. Here's a 3-dimensional vector. Vector v is 2i plus 3j plus 5k, meaning you go forward 2 to the right 3 up 5, and that's the vector. Connect the dots. That is the vector. From 0, 0 to 0.235. That would be the vector in space. Great. How can you tell if this vector is parallel to any of these? How do you tell if that vector is parallel to any of those vectors? Yes? It is a direct extension. Nothing changes. You just add in a c squared. Side note to that, in terms of 3-dimensional vectors and whether or not they are parallel or not, in 2 dimensions, we know that 2 lines are parallel if they have the same slope, right? We also say that as they're parallel as long as they're off the same line and they don't intersect, right? If in 2 space, if 2 lines are not identical and they don't intersect, they have to be what? They have to be parallel. Is that true in 3 dimensions? Ah, is it? Hold out your arm. Straight. Ready? There's a vector. Make it a little angle right there, right? Ready? Here's another 3-dimensional vector. Are they parallel? Are they? No, I mean, like, look at all these vectors right here. Are any of these touching? Are they ever going to touch? Are they parallel? No. We're going to get to this later. They're called skew lines. In 3 dimensions, you can have 2 vectors. See all these vectors right here? Do they ever touch? No. Are they parallel? No. So that's something where it changes. Here is something where it's just a direct extension. But in that case, it breaks. Remember? 2 dimensions. It's either concave up or concave down. But with a hyperbolic paraboloid, you can get both. And you're like, what? What? Okay, can someone tell me what they see here? What do you see when you look at this? Is this a unit vector? Is that a unit vector? Does it have a magnitude of 1? Oh, come on. No. What is, you just say it. Like, you're like, I don't, what is the magnitude of that? It's the square root of 1 squared plus, so it's the square root of 10. Not 5, 10. So is that a unit vector? No, it's not. Can you tell me what the unit vector is going in the v direction? So what is the unit vector in the v, or not in the v direction, I could say unit vector, yeah, in the v direction. Can someone tell me what it is? You have all the information you need right there. What's it going to be? What's it going to be? I plus 3j all over what? Root 10. Exactly. So a way you could write this is, you could write it as 1 over root 10i plus 3 over root 10j. That's one way to write it. What's another way to write a vector? Just the what? Just the components. So it would be 1 over root 10 and 3 over root 10. Now, can you check to see if that has that is a unit vector? Sure, it should be, because what's this squared plus this squared? Over 10. What's 10 over 10? 1. So what's the magnitude of this vector? 1. The magnitude is 1. Did we change the direction? No. When you multiply or divide by a scalar, can you change the direction? No, unless it's negative, it flips it around. So it's still going to go. It's still going to be a unit vector. And also, because we're dividing by a magnitude, the magnitude is always what? Magnitude is always positive, because speed is always positive. Yay. Nice. We're not going back in time yet. I'm not going back in time yet. Okay, so I put something